Take a look at this textbook cover, Hoffman and Kunze's Linear Algebra. If you are working your way through Chapter 8, you are building toward a very specific, highly structured target, normal operators. This single equation on screen is the defining test. An operator T is normal if and only if it commutes exactly with its adjoint, T star. The general goal in linear algebra is often finding a basis that makes a transformation matrix diagonal. We are smoothing out a skewed coordinate system so the resulting computations become manageable. But the absolute ideal scenario is achieving this with an orthonormal basis. Notice how the axes here lock into perfect right angles. Every vector in the basis is exactly perpendicular to the others, and each has a length of exactly 1. This equation is the specific requirement for that geometry. If an operator satisfies this commutative property, then and only then is this exact orthogonal layout guaranteed to be possible. We can map how normal operators relate to what we already know using this hierarchy tree. At the top, we have normal operators. One major branch falling directly under this is self-adjoint, or Hermitian operators, where T equals T star. Because any matrix commutes with itself, self-adjoint operators pass the test by default. A second major branch covers unitary operators. For these, multiplying T by its adjoint yields the identity matrix. Because the identity matrix commutes with everything, unitary operators also fit perfectly under the normal umbrella. To see the mechanics behind this, look at this mathematical relationship from Theorem 19. If a vector is an eigenvector of T with eigenvalue C, it is automatically an eigenvector of the adjoint T star with the complex conjugate of C. Because the operator and its adjoint share these vectors, taking the inner product of two eigenvectors with different eigenvalues forces the result to 0. This mathematical interaction is what physically drives these vectors into a strictly orthogonal arrangement. By expanding beyond real symmetric matrices to include complex spaces with complex eigenvalues, we retain that exact perpendicular structure. We just use normal operators to prove it. This brings us to the ultimate payoff in Theorem 22. Look at this diagonalization equation. Every normal operator on a complex inner product space has an orthonormal basis of eigenvectors, allowing us to form this diagonal matrix D. Here is where the computation becomes remarkably efficient. For normal matrices, the transition matrix P is unitary, meaning its inverse is exactly equal to its conjugate transpose. You skip the tedious process of calculating a full inverse matrix. You just transpose and conjugate. Let's test this in practice. Take a close look at this 2x2 rotation scaling matrix A, alongside its conjugate transpose, A star. We need to verify if this matrix is actually normal. Grab a piece of paper, pause the video here, and manually compute A star and A star A to see if they match. Working through the rows and columns, multiplying A by A star yields A squared plus B squared on the diagonal and zeros elsewhere. Reversing the order to A star A gives us the exact same result. Even though our original matrix is not symmetric, proving that it satisfies this commuting property guarantees it can be perfectly diagonalized over the complex numbers. Let's summarize the 3 core properties on a quick cheat sheet. First, the definition. T is normal if and only if it commutes with its adjoint. Second, the categories. The normal family directly includes both self-adjoint and unitary operators. And third, the geometric result. Normality ensures you can construct an orthonormal basis consisting entirely of eigenvectors. Mastering this single commutative property provides the structural foundation for the most efficient transformations in linear algebra. If this breakdown of Hoffman and Kunze was helpful, please like and subscribe for more linear algebra tutorials.